So we will start the class. So in the last week's class, we stopped talking about we stopped at a point where we discussed about the generation of the electromagnetic waves and how they are generated in the real world. If we use like a varying, if we have a varying current in a certain metal conductor, then we can create a certain varying magnetic field which will be created around the metal conductor, and due to the varying current, the magnetic field that is generated will also be varying with the time. After that, we can also say that a varying electric field is generated at each point of the varying magnetic field. Okay. So last time I can remember that you asked about like how the electric field is generating at each point, right? 360, yeah, at each point in this loop. Okay, so at each point, yeah, it is generated, and we can actually draw electric field at each point in this loop. So we can draw electric field for each point in the loop. So if we draw like this, for example, for each point, I can draw. In this situation, electric field generation like this will create magnetic fields which are perpendicular to those electric fields. So for each of these electric field loops, a magnetic field will be generated. So it is going to be complex if I'm going to draw for every loop. So I will only consider one loop. So for the question that you asked, so this wave will be created in all directions, and in that case, we call that this wave is propagating just like an isotropic antenna. Okay, isotropic. You know isotropic word? In all directions. In all directions. In all directions. So it means like in 360. In all directions means in all angles around the 360 degrees. So in all directions, the radiation will happen. Okay, so in all directions, wave radiation will happen and wave propagation will happen based on the electric field strength and the magnetic field strength that created it. Okay, so so if we consider one point and evaluate or analyze that point in the, for example, if we consider one point in the magnetic field loop and consider the electric field that is generated due to that point, we can form a loop of chain of electric and magnetic fields. Okay, so if we if we want to detail it further, we need to use the right hand rule to find the direction of the magnetic field and then the electric field. So first we can find the direction of the magnetic field using the right hand rule around the metal conductor. So by keeping the thumb along the current direction, I can find the direction of the magnetic field along the fingers of the hand. So So we can see the direction of the magnetic field will be like this. Yes. So so once we take the magnetic field, based according to the specific point we consider in here, the magnetic field is going inside the uh, paper, right? Yeah, into the paper. So in that case, now we need to select the thumb along the magnetic field direction. So we can see the electric field is going in this clockwise direction. So electric field will be in this direction. So again, we can take a point in the electric field loop, which is in this plane, and then we can select that point in here. Okay, so the same plane. Okay, so I will try to erase this one. So if we take this plane and the kind of the middle point of the electric field, then I can see the electric field is going down. The electric field is going down in this point in here, right? Electric field is going down means like magnetic field is rotating in this direction. So magnetic field will be generated in this direction. Is it clear? Yeah. No, they are not equal. The second one is created by the electric field that is generated in between. So this will be different. This magnitude B will be different. The initial magnitude of the magnetic field will be B1. This is B1, this is B2, this is E1, likewise. So B2 was created by E1. Okay, so likewise, we can actually evaluate of all the points, and we can say that a chain of magnetic field and electric fields are generated because of their relationship. Like because of electric field, magnetic field is created. Because of magnetic field, the electric field is created. So for this as well, we can draw something like this. Its magnitude will be different. So this will be electric field, and its direction can be determined by the right hand rule. So we can draw like this forever until it dies. Until it dies, we can show that wave will be present. So likewise, this will go on like this. Okay. So this behavior we can draw in a certain plot where we draw the magnitude of electric field and the magnetic field. Okay, so electric field, if we take into consideration along this axis, we can consider how the electric field is varying, and we can see that electric field is with the distance is varying according to a wave. Okay, so the magnitude of electric field is reaching from 0 to a peak point, and then it is changing its direction, and then it's moving in that direction, and then again reversing its direction. So the direction of the electric field is given by the direction that we find in here from the right hand rule. Okay. Yes. So electric field will be created like this. Yeah, so magnetic field will be also increasing its magnitude and decreasing its magnitude. So it's like we can't. uh, yeah, the direction of the, yeah. So but I mean, we can't really relate it like that. We can't say the magnetic poles are changing like that. But the electric field is what is creating the magnetic field. Based on the electric field direction, the magnetic field's direction changes. If the electric field reverse its direction, then as a result, the magnetic field direction is getting reversed. So the magnetic field magnitude and direction depend on the electric field, which causes it. Yeah. Yes. Hmm. Yes. Magnetic field from north to south, north pole to south pole. And what I'm saying is, once the electric field's magnitude is reducing and it's changing its direction, then the magnetic field's direction also is changing. So so this happens without the presence of north pole and south pole in the matter. We don't have a magnet, but the magnetic field is created by electric field. Yeah. Yes. So you have to draw a wave like this, which actually which shows the electric field variation and the magnetic field's variation. So I think I need to draw it properly. First, you can draw the electric field and then you can draw the magnetic field. So once you are drawing the magnetic field, the magnetic field must be drawn in a certain angle so that we can properly show its difference with the electric field. So I can draw like this, the the magnetic field. So I draw with these arrows the magnitude of the magnetic field and the magnitude of the electric field. You mean what? Mm. Yeah. Yeah, we cannot say that they are equal based on uh, the field that created it. Only it depends. So we actually learned about how curl of electric field is created due to the rate of change of magnetic field, right? So based on this rate of change of magnetic field only, the magnitude of electric field is depending. So because if this rate is not enough, then electric field will not be high enough. So likewise, the magnitude of the magnetic field is depending on the rate of change of the electric field. There are other parameters also, but mainly this is one of the reasons for the magnitude of the magnetic field to change. And if the electric field is not varying with a certain frequency, the magnetic field will not be strong. So yeah, so it depends on the conditions of the field that 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 is creating the magnetic or the electric field. So we can actually draw the waves like this, which shows the electric field and the magnetic fields uh, and their directions. Okay, so I don't know whether I will use another color to show the other direction. So electric field I will denote using another color. So electric field I will denote like this along the x z axis. I mean x. Sorry, in this direction. So we will take this axis as. I mean there are different ways of showing it. So if we take this as x direction, and then I don't know if it's correct notation. So I think you can draw the wave. You can draw the wave. So another important thing is like the wave is propagating along the perpendicular direction to both the electric field and magnetic fields. So the wave is along this direction. Wave is along this direction. So wave propagating along the direction which is perpendicular to both the electric and magnetic fields. Okay, so basically that is regarding how the electric field and magnetic field will generate a propagating wave along a direction which is perpendicular to both electric and magnetic fields. Okay, so this is something visual that we discussed. Yeah. Yes. Yes. Cross product should be along the perpendicular direction to both the E and H, E and B fields. So that is, yeah. So if we take the cross product between the electric field and magnetic field, we can get the direction of the wave propagating. Okay, so E from E to B, if we move our finger, we can see the wave direction along the thumb direction. So so that is regarding how we can visually visualize the generation of a wave. Now we can prove mathematically the generation of a wave, and we are using Maxwell's law to do that. Okay, so Maxwell's law we learned by spending a lot of time to mathematically prove the existence or the possibility of the generation of electromagnetic wave using electric and magnetic fields. So we are going to mathematically prove that in this class. Okay, so I'm going to erase this. Sorry, electric field to magnetic field. So actually now magnetic field also can create electric field. Okay, magnetic field also can create electric field. It's totally fine. But the thing is, like always, we cannot find these magnets. However, like it's easier to find electric charges. For example, in the nature. It is easier to find the existence of the electric charges. For magnetic, field to exist, we need to find a permanent magnets, like materials with that magnetic property. Yeah, varying magnetism is hard to find. Therefore, we are using electric field, or we are using the varying current as the initial point of generating electromagnetic waves easily. Easy method, varying current, generate varying magnetic field. So that is basically that. I will erase this. So mathematically, we can prove that a wave is generated. So for that, we are deriving the wave equation using the Maxwell's laws. So so we use, so I will write deriving the wave equation using Maxwell's laws. So we learned Maxwell's law to mainly prove the existence or the uh, presence of electromagnetic waves, and we can show it mathematically using that. So we can derive it using the laws, but first we need to make some assumptions. So anyway, first, I will write one sentence. So we use Maxwell's law to prove that a propagating wave, propagating EM, electromagnetic, to prove that a propagating EM wave is generated. EM wave is generated due to the interaction, between electric and magnetic fields. Right. So in order to derive this fact, the fact that electromagnetic wave is generated, we need to make some assumptions. So the assumption is that wave is propagating in a certain homogeneous medium. With permittivity. So the wave is propagating in a homogeneous medium with permittivity of epsilon, and permeability mu. So we are assuming that the wave is going through a homogeneous medium. So homogeneous medium means what? Sorry? Curl is 0. Homogeneous means like word means like the material inside that medium is uniform at each point in the medium. If you take, for example, pure water, glass, or some kind of a material which has the uniform composition all at each point of the medium. So there's no variations in the densities, the particle concentration. There's no variation at different places, but every place is having the same density, same configuration, or like concentration. Same features are there at every point of the medium. That is what is mean by homogeneous. Yes. Permittivity will be constant throughout the medium. So what is the meaning of permittivity? So, I mean, permittivity is defined as the ability of a certain medium to create electric field. Ability of the medium to, create electric field and store the electric potential within the medium. Okay, so ability of a medium to store electrical energy within the medium. Within the medium. So the meaning of permeability is what? So permittivity is regarding electric fields. Permeability is regarding magnetic fields. So permeability is the ability of a medium to generate uh, generate or form magnetic fields within the medium. Okay, so that's regarding the assumption that we are making. We are assuming the wave that is propagating is in propagating in a homogeneous medium with certain permittivity and permeability. So whatever the wave is generated, it is moving in a homogeneous medium. We don't know what kind of a wave is generating, but we are going to find it using mathematics. Not because of this, but because of another assumption we are making. We are going to assume that this wave is propagating in the free space. Free space, yeah. Yes, so yeah, if it is moving in the free space, then there's no interference from the medium or any interference from other like forces in the medium. So therefore, like there's no interference means the wave does not deteriorate. The energy does not decrease. So it is not natural. It is just a theory, like assumption that this kind of thing behaves in free space like this. If it is like that, then we can do more calculations, or like we can keep it as a baseline, and then we can improve on it for other situations where there's medium, where there's interference, so on and so on. So the basis is the assumption that it is traveling in the free space without any attenuation. So as the first step, we are going to also assume that the wave is propagating in free space. Okay. So wave is propagating in free space. In free space. Okay. So the word free space means there's no like matter or particles, but there's the ability for the free space to accommodate fields like electric fields, magnetic fields can be present in the free space, but the free space is like vacuum, but in vacuum, like there's no particle or there's no matter. But in free space, in free space also there's no matter, no particle. The difference is that it's possible for fields and forces to exist in this medium. Fields are existing. So fields can exist. So fields can exist. So fields like electric field, magnetic fields can exist in the free space. So vacuum is a place where nothing, including fields or forces, can exist. So in vacuum, basically no particles, no fields. So the ability is not there for like a field to form in that region. So in there, actually, we cannot consider the wave propagation phenomena. So we are not considering the vacuum actually. So yeah, in the free space, there can be electromagnetic fields in the free space, but not in the vacuum, I think. So there's a difference between these two terms. Maybe you can search on that. Okay, you can search more on this, whether gravitational field can exist in vacuum or not. You can search on that. In free space, gravitational fields and electromagnetic fields can exist. So in free space, particles are not there. Particles do not exist. Matter do not exist. Different types of fields can exist. So these are the assumptions that we are making. Okay, so I'm going to erase this. So for a perfect homogeneous free space with the with permittivity of epsilon naught and permeability of mu naught, then we can write from Faraday's law that the existence of a curl of electric field is due to the rate of change of the magnetic field with the time. Okay, so this one we already discussed under Faraday's law, right? We discussed that once we are changing the electric magnetic field across a certain loop of metal loop or something, then based on the rate of change of the magnetic field, the amount of electromotive force that is generated around this loop is changing, and the potential is generating in the opposite direction to the magnetic field change, the direction of the magnetic field change because of the Lenz's law. So anyway, so based on this equation, we can improve on that. We can take the curl on both sides. Take the curl on both sides means we are going to add the curl operation on both sides. Curl operation means you are going to add this, delta into this cross product. So this part we call as curl function, and then we are adding it onto this available equation. Right, so if we are going to add it on to both sides, we are going to put it inside this derivation or differentiation, and we will be putting it inside this differentiation like this. So we have taken the curl operation, which means like we are adding this cross product. Not the Laplace, but the curl function, curl of a certain function, we learned that it is like this, right? So the curl of the certain function, we can I, J, K likewise, and then we can write the components of the force F1, F2, F3, and then we can take the determinant of these two things, right? So first we need to write the first we need to write the W over W X, W over W Y, W over W X, and then we need to write F1, F2, F3, and then we take the cross product. Okay, so this is the function in here, right? So this function is something that we can add this operation on top of. This is the operation of the curl. So the curl operation is this. We are adding that curl operation onto a certain function that we already had. Okay, so to both sides, we are adding the curl operation. So mathematically, once we are having this kind of expression, we can deduce it further, and that it can be deduced into this manner. So it is coming under mathematical operations, and we can write that final expression as this delta dot E equals, minus, now we come actually to the square of the delta, which is actually the Laplacian operation, as I think we discussed. So anyway, we can write the mathematical equivalent of this left hand side as according to as this expression, and on the other side of the equation, the same expression remains. Yeah, it is just the, no, it is the dot product actually, I think. We can convert this cross product, expressions into a dot product minus the Laplacian of the electric field. So this dot is actually the dot product. You can actually search on this. So you can refer the book that I have provided in LMS as well, and then you can refer like how they have deduced this equation, and you can let me know if there's some difference. So both the sides we have. So we have the expression like this. So so now we are left with this. So I will try to erase this. Have you written all this? I'm going to erase this. So I'm left with this. So if we take a free space, the amount of electric charges in the free space is what? What is the electric, do we have electric charges in the free space? So what is the value of this divergence of electric field? 0, right? So we learned from Gaussian law that the divergence of electric field is equal to the charges stored in the space. Yeah. So if there are no charges in the free space, the divergence of the electric field is 0. And therefore, so this is basically because there are no free electric charges in the free space. Right? So because of that, we can also write from Ampere's law that the formation of the magnetic field in the free space will be equal to 0 plus mu naught epsilon naught into W E over W T. So this 0 is coming from the fact that mu naught J is equal to 0. The charge density is also 0. So therefore, now we can use these results in this equation that we derived earlier. So in A, we can substitute these results or assumptions. Then in A, we can write now a dot product of electric field is with the divergence of electric field is 0. Therefore, this first expression is going to be equal to 0. So we are left with this expression, and on the right side, we are left with dabba over dabba t inside the brackets mu naught epsilon naught dabba e over dabba t. Right. So this one we can write further by cancelling out the minus sign of both the sides, and we can write a clean expression like this. So we can take the mu naught epsilon naught outside, and we can write that the differentiation is to the power of 2, and then the electric field is varying like this. So this is the equation that we are left over after doing simplification of the expressions. So the electric field is behaving in this manner. Okay, so electric field is available on both sides of the equation, right? And also we can equate, we can see this same type of equation available in the physics to describe the wave equation of like materials. The wave equation in wave equation. So wave equation in physics show a similar behavior. Physics show a similar behavior or a similar model. Yeah, we can write using these in a similar manner using these terms, operations. I will write that. So the classical wave equation that we have, I will write that. So the wave equation in the classical physics will be this velocity squared dabba squared over dabba t squared. The second derivative of the displacement of a certain wave along the time, second differentiation is equal to the actually the Laplacian function of a certain displacement of a certain wave. So if we take the wave equation, waves propagating in a certain material with a certain displacement y, then that equation, that wave can be described using this equation. The displacement is given by y. Okay, so the displacement, I do not point out the peak in here. Just any point, sorry. Any general point, we can denote the displacement using y. So y is the any displacement along the any point in the wave, and that y will be equal to this. That will be following this equation. So basically, mathematically, we can denote a wave using this equation. So we can see that a similar equation is obtained by the electric field. Once we look at this equation, the same type of behavior or same model is same model is shown by electric field as well. That means that the electric field is moving as a wave, right? So electric field shows the behavior of a wave. So electric field is moving as a wave. So shows a wave-like behavior, right? Also, we can write the same thing for a magnetic field also. Right? Similarly, we can write for this magnetic field also. Yes, magnetic field also a wave. So similarly, we can derive using Maxwell's laws. Using Maxwell's laws, we can derive the fact that the magnetic field is also following this expression. Okay. So however, I'm not sure whether I need to check whether this is H or B. Okay, so in here normally we use either B or H. So B equals mu naught H, right? So in here it could be H because of the presence of the mu naught and epsilon naught outside this expression. Okay, so instead of B, we will use H in here. So it is basically because of the mu naught epsilon naught. And if we get them together at one point, then we can actually write B also in this equation. We can substitute B also into this equation. So basically E and M will be, E and magnetic field will be following wave-like behavior. And because of that, we can also equate, we can also get another important parameter regarding electromagnetic waves, which means that the constant value in here, which is 1 over speed of the wave. Now Vp is the speed of the wave speed. So right, so this parameter we can equate in both the situations, and we can write that the speed of the wave is equal to mu naught epsilon naught, right? By taking the equations A and B. Let's say this is A and this is B. So considering A and B, from A and B, sorry. Yeah, they are constants, and since these expressions are showing the same wave-like behavior, yeah. So because they are showing the same wave-like behavior, the speed shown in this one also must be related to the speed of the electromagnetic wave in here, right? So we can actually, I mean, this is not the speed, but this parameter can be used to equate and find out the speed of the electromagnetic wave. So the electromagnetic wave's speed can be found by equating these two parameters, right? And then the electromagnetic wave's speed can be found by taking the square root of mu naught epsilon naught 1 over square root mu naught epsilon naught. Okay, so since in the classical wave equation, this parameter, this constant parameter is related to the speed, we can actually by similarity, we can say that this equation also, this constant parameter can be equated to this one. So so by doing that, since we know the velocity of the wave is given by this constant, we can relate this somehow to the mu naught epsilon naught. And then by doing that, we can find that the wave velocity can be defined by the epsilon naught and mu naught. Sorry? Yeah, in free space. So in free space. Okay, so you know the value of mu naught and epsilon naught, and that by substituting that, you can find the velocity of the electromagnetic wave in the free space. So once you substitute that, you will be able to find that Vp, or the velocity, is equal to actually 3 into 10 to the 8 ms minus 1. Okay, so that means the light speed of light. Right? So the electromagnetic waves in free space travel with the speed of light. So with that, I end today's class.